Yo, what's up everyone? Welcome to States of Matter Part 7. Today we're going to be talking about liquids. So on a molecular level, this is what a liquid looks like. The molecules are kind of close together, but they're farther apart from each other than they would be in like a solid. So the molecules in a liquid are allowed to move around a little. They can move around a little in the space that they are. Um, Unlike a solid where the molecules can only vibrate in their position, but they can't move as much as, say, a gas can. So that's what they look like on a molecular level. Let's look at some properties. First of all, they have definite volume. And although they have definite volume, they have indefinite shape. So this means a volume that you take from a water bottle, you can pour that into like a jug or something. The volume will stay the same, but the shape of the liquid, of course, changes. Three, they can be slightly compressed. And the change in pressure associated with that is minimal, but the pressure required for that is really a lot. It requires a lot of pressure just to be compressed a little bit. And four, you have surface tension, and five, you have capillary action. We're going to go over both surface tension and capillary action in a bit more depth, starting with surface tension. So surface tension is the resistance of a liquid to an increase in its surface area. It's the reason if you've ever seen a car getting waxed, always when you put water on top of it, it kind of like beads up. The reason is because of surface tension. The intermolecular forces in the water want to stick together, so they kind of resist the urge to increase in its surface area. But of course, after a while, it kind of just I guess reaches its maximum and it just breaks apart. And so as you increase your intermolecular forces, your surface tension increases. So for water actually has pretty high intermolecular forces. That's why it has such high surface tension. So if you were to fall like 40 feet into water, that would hurt a lot because of surface tension. When you hit the water, that would be like hitting concrete or something. It won't be like you just splash in. It's gonna hurt, and it's because of surface tension. Capillary action is next. Capillary action is the spontaneous rising of a liquid in a narrow tube. So if you look at the diagram on the left, you have two water pipes, and the water in the thick pipe went up less compared to the water in the thin pipe. Capillary action usually happens in polar molecules, such as water, and it occurs due to two things: cohesive forces and adhesive forces. So cohesive forces are the intermolecular forces between the molecules, and adhesive forces are the forces between the liquid and the container. So what happens is that the water on the edges of these tubes, the waters over here, kind of get lifted up from the adhesive forces. So the force between the liquid and the container kind of lifts that molecule up. And what happens is that when that molecule gets lifted up, the cohesive forces jump into action. So as that molecule goes up, the molecules around that go up, and so on and so forth. That's why you have this like meniscus, you have this parabola shape here, because this is just a mixture of adhesive and cohesive forces. And that is capillary action. It occurs naturally in plants. This is how plants get their water from their roots all the way up to their stems and stuff. So they use capillary action to make all of this happen. And they use like really tiny tubes so the water goes up really fast. Yeah, that's capillary action. Let's talk about vapor pressure. So in a normal in a normal liquid, you have all of these molecules. And these molecules are all moving at relatively different speeds. Let's say their distribution of kinetic energies, how fast they're moving, is represented by this curve. Now, this curve is going to have a certain threshold. If a molecule has enough energy, it can jump up from the liquid and become a gas. So if a molecule were to have enough kinetic energy, it could break that barrier and become a gas or become this vapor. So let's say that the energy needed to escape the liquid is about right there. Molecules that have more than that kinetic energy can lift up and become a vapor. And so if you were to increase the temperature, what would happen is that the average kinetic energy would change. The threshold would stay at the same position. It's just that the average kinetic energy that every molecule has increased, so more molecules have hit the threshold. And so you have more and more of these if more and more of these liquid molecules turning into gases, and you have this vapor on the top. Now, when you're at equilibrium, when your rates of condensation and vaporization are equal, the vapor pressure on this top area is what you call the equilibrium vapor pressure. It's the pressure of the vapor at equilibrium. Sometimes we just say vapor pressure instead of saying equilibrium vapor pressure, but they refer to the same thing. And so you're going to have two different types of compounds that you can classify based on vapor pressure. So you have volatile compounds, so these are compounds with high vapor pressure, and you have non-volatile compounds, which are compounds with low vapor pressure. So what's the relationship between vapor pressure and the boiling point? Well, when the vapor pressure is equal to the pressure of the atmosphere, you have reached the boiling point. That's why they say it's easier to boil water on top of Mount Everest. That's because the pressure there is lower, so you are going to reach your boiling point at a lower temperature, meaning you can boil water faster. So when vapor pressure is equal to the pressure of the atmosphere, you have reached the boiling point. And that's it for liquids. I hope you were able to learn something. I hope this was helpful, and I hope to see you later. Thank you for watching.